logistic, linear, and Cox in the coming weeks. But there are other types of outcomes, too, that have their own types of models, too. And we probably won't have time to talk about each of them in enough detail. So we'll talk about a few of these different types of regression models. And remember, what that means is different types of outcomes of interest, categorical, ordinal, or continuous. So let me give you the general formula. If you have a binary outcome, this is what we'll talk about next week. We'll talk about logistic regression models. This type of model is appropriate if you have a binary outcome. The focus is on the risk P of developing an outcome category of interest. Risk of dying, as in the previous example, the risk of being anxious if you're trying to build a model that who's anxious and who's not anxious. The outcome of interest is the risk, the probability of developing that outcome category of interest, the risk of dying, the risk of developing anxiety. The coefficients, all these x's again are risk factors. It turns out that the risk factor, x sub I, the coefficient of x sub I, v sub I, in general measures the adjusted effect of that risk factor on your outcome, controlling for everything else in the model. In particular, it's adjusted measure in terms of being an adjusted odds ratio, as I showed a few minutes ago. So all these coefficients in the logistic regression model are adjusted log odds ratios, or the log of the adjusted odds ratio, pertaining to increasing that risk factor by 1 unit. Well, if your risk factor was cancer, coded as 1 and 0, the only way you can increase that by 1 unit is to go from not having cancer to having cancer. So for cancer, this was the odds ratio of cancer patients versus non-cancer patients. If X was age, this would be the effect of changing from 40 years old to 41 years old, or 50 to 51, and 1 year increase in age. So it would be the odds ratio comparing two people, one person who's 1 year older than the other person. If you get rid of the log by taking the exponential function, e to the beta 1 becomes nothing more than the adjusted odds ratio. That's how we control for confounders when we have a binary outcome by using logistic regression models. And to give you an example, this is some data that's available on the web. It's data, a subset of data from the Framingham Heart Study. There's a famous heart study in Honolulu, in Hawaii, the Honolulu Heart Study. The Framingham Heart Study was done in Framingham, Massachusetts. I think I mentioned it. It enrolled about 5,000 people back in around 1950. They planned to follow them for 20 years to see who develops heart disease and who doesn't. They planned to see whether smokers get more heart disease than non-smokers, whether high blood pressure people get more low blood pressure people. And basically, the study is still going on. It's been going on for 50 years now, and still following people who are still alive to see who does and who doesn't develop heart disease. This is a subset of the original data, 1,406 people. Actually, a subset of that, only the 1,363 people who didn't have coronary heart disease at their baseline exam. This is looking at the risk of developing coronary heart disease during the lifetime of the study. Anybody who already had heart disease when the study began was no longer at risk for developing heart disease for the first time. They already had it. So those people were excluded from the analysis we'll look at today. So the analyses are based on these 1,363 people at risk of developing heart disease during this study. These are some of the risk factors we'll be looking at. The outcome is whether a person develops heart disease, new CHD. So it's coded as a 1 if you develop heart disease during the follow-up period, 0 if you didn't. One of our risk factors of interest is the gender of the person. And it's coded as 1 if you're a male and 0 if you're a female. What we'll be talking about probably on next week is talking about confounding by age. So age is something we're going to look at either measured in years or breaking people up into two groups. Older than 55 or under 55. 55 was the average blood pressure and the average age in these people. That's why I made two groups above and below the average, actually the median, above and below the median. Another variable we're going to be looking at is smoking. They recorded the number of cigarettes a person smoked at their first exam. We made that into a PAX variable. Anybody who smokes 0 cigarettes is called a 0 for PAX. Anybody who smokes between 1 cigarette a day up to 20 cigarettes a day, well, that's a 1 pack a day smoker. They open up 1 pack a day, 1 pack of cigarettes each day and smoke some of them. The 2 pack a day smoker is anybody who smokes 21 to 40 cigarettes a day, and a 3 pack is anyone who smokes 41 to 60 cigarettes a day. And there wasn't anybody who reported smoking more than 60 cigarettes a day. I also made 3 indicator variables, 1, 0 variables, to indicate whether a person was a 1-pack-a-day smoker, or a 2-pack-a-day smoker, or a 3-pack-a-day smoker. So, for example, PAX 3 is a 1 for everybody who smokes 3-pack-a-day cigarettes, 3 packs a day cigarettes, 0 for everybody else. PAX 2 is a 1 if you smoke 2 packs a day, 0 otherwise. 1 pack a day, PAX 1 is the one who smokes exactly 1 pack a day, 0 otherwise. Let's look at some of the analyses we talked about last week. First, we'll look at this binary outcome, developing NECHD, with a binary risk factor. Binary risk factor I'm going to use is male. So this is a printout from SAS. 2x2 table. The first row are the males, male equals 1. The second row are the females, male equals 0. The first column are the people who developed NECHD, NECHD equals 0. Second column are people who did develop NECHD, NECHD equals 0. So we see, for example, there are 643 men in this study. 164 of them developed NECHD during 20 years of follow-up, actually 18 years of follow-up in this data. That means 25% of them developed heart disease during the study. Let's call that their risk of developing heart disease. There were 720 women, 104 developed the disease. That's 14% of them. So a woman's risk was 14%. Now, last week we talked about different types of inferential statistics we could do from this data. We could do tests of significance. We could do a chi-squared test. So, for example, if you looked at this data and said, how consistent is this data with the null hypothesis that men and women have the same risk? So the chi-squared test would lead to a p-value that's very, very small, less than 0.001. SAS gives you a number of tests, a number of chi-squared tests. Notice the first 4 tests here all have very similar test statistic values, about 25 or 26. All their p-values is less than 0.01. Is the usual chi-squared test that we talked about last week. It also gives you a Fisher exact test. For every 2x2 table, it gives you a chi-squared test, and it also automatically gives you a Fisher test. The p-value from the Fisher test is 3.83 e to the minus 0.07. What that means is take the number 3.83 and move this decimal place 7 places to the left. So the answer would be 0.000000383. Clearly, that's less than 0.0. So if you go back to that 2x2 table and compare the 25% risk among the males to the 14% risk among the females, by dividing 25 by 14, you'll get a risk ratio which is equal to 1.7658. You can also calculate an odds ratio from that 2x2 table. It's 2.02, and that's what I'm going to be focusing on today, the odds ratio. And it builds you a confidence interval around that odds ratio. It goes from 1.54 up to 2.0. If you can, just remember these numbers, 2.02, the confidence interval. If you can't, I'll remind you of them. Remember this chi-squared test, this test statistic of 26.375, and very, very, very tiny p-value. Because we're going to see them again when we talk about regression models. But let's suppose your outcome was not binary, but was categorical, like PAX. What you could do is build a table that doesn't have 2 rows to it, but has 4 rows to it. 1 for the non-smokers, 1 for the 1-pack-a-day smokers, 1 for the 2-pack-a-day smokers. It says, for example, you've got 748 non-smokers. 134 of them develop disease. That's a risk of 17% on average among people. Compared to the 1-pack-a-day smokers, 487 of them, of which 99 developed disease during the follow-up. That's a higher risk of 20%. So notice your risk goes from 17% up to 20% when you move from the non-smokers to the 1-pack-a-day. When you move to the 2-pack-a-day smokers, it actually goes up even higher to almost 30%, 29%. But notice when you move to the heaviest smoking categories, your risk of heart disease actually falls below the risk in the non-smokers. So a mental question, do these data suggest to you that lots of smoking is good for you? In other words, a little bit of smoking, 1-pack-a-day smoking, increases your risk of developing heart disease. More smoking, 2 packs a day, increases it more. But does this data suggest to you that smoking a lot, 3 packs a day, actually decreases your risk? Would you say that this data supports the hypothesis that heavy smoking is protective? Well, we'll get back to that question in a minute as you're trying to formulate it in your mind. But notice there's no single odds ratio, risk ratio you could calculate here because you have 4 risks, not